Well, good evening, good morning, good afternoon, everyone. Welcome to Ellensburg, Washington, USA. Thank you for joining us. This is a live stream. It's 11:47 a.m. Pacific Time. You say Pacific Time. You say International Pacific Time. Are we 5 by 5? Are we functional? A delay in the comments. Peter's chiming in with a 5 by 5, and Tim says we're good as well. Let me get on screen. Can I read the title slide to you? I think you can read, but just in case you cannot. We're looking forward to an ice core lecture today. High resolution, hyperspectral, microphysical, and mineralogical analyses on the ADA 270 Adamello ice core from the Italian Alps. We have a very special guest, Debra Fiorini, and you will get introduced to her momentarily. I stumbled because I just saw Sharon says no video, but I think everybody else can see the title slide, at least I hope so. Let's get on camera and say hi to a few of you, and then we'll swing you around and enjoy the room. Hi everybody and welcome. Thank you for coming today. Hope that you enjoy this lecture. We want to continue to make sure that we are 5 by 5. Where are you viewing from today? And I'll keep an eye on making sure that we're loud and clear. Garrett from the Netherlands, Pam's in Bitterroot, Montana. Bryce is a star. That's what it says here, Bryce. Menominee, Michigan. Sunny Seattle. Yeah, it's sunny everywhere up here in the Northwest. It's absolutely perfect outside. We should all be outside right now. Where are you viewing from? Media, Pennsylvania, Marysville, Washington, Michigan, Northern Indiana, Christchurch, New Zealand, hello Rob, Vancouver, Washington, Northern Illinois, Springfield, Oregon, Adele, Disco Park, Washington, Cologne, Germany, Dayton, Ohio, Michael says good evening from Kilkenny, Ireland. Hi Michael, maybe with family as well. Marco in Portland, Oregon. Yeah, as soon as this is done, I'm heading straight to Portland to give a talk tonight. Maybe I'll see you tonight, Marco. Sharon from the Malaga Slide, John Nash from Hubbard, Oregon, Mission Hills, Los Angeles. Thank you for the report. And so on. We're approaching 100 live viewers, and folks will continue to trickle in. Let me turn the camera around. Looks like, oh, you know what? We're going to test. I'll turn the camera around. You'll get a chance to see the room fill in. It's such a beautiful day. We're not going to be at capacity just because of the weather more than anything else. And I will eventually put a second microphone on Debra. We'll make sure that we can hear her. And one little wrinkle, just to let you know, we're going to have Susan introduce the speaker today. So I'm going to hand this mic over to Susan, and she's going to do the introduction for the speaker. So we'll see if that works today. Okay. Thank you for being with us. If you are not live and watching this recorded video, we're going to start the lecture in 10 minutes, and you'll see a chapter title showing you exactly where the lecture begins. You'll be able to skip to that. Thank you. You got it. Thanks. Good, guys. How are you? Good. Hello.
How are you?
I'm doing well. David? How did it go yesterday? Wednesday. How did it go on Wednesday?
My first section was really, really well. Like, they enjoyed it so much. Like, we left a little late because they were
Oh.
taking rock from the outcrop.
Good.
But the second section wasn't.
A dud.
Yeah, they weren't as excited about it. We left early even. So it's like,
That says it all. Like every group has got their own personality at this point.
So the first one really enjoyed it.
Good.
I had a good time with it.
Good.
And it was such a beautiful day. No wind. It wasn't even that hot.
Excellent. Well, there was a lot to unpack at that outcrop, and if you felt like you got a bunch of the stuff across, was it mostly group stuff, or were you kind of turning them loose for the most part?
10 students, so they got into groups of 5.
Yeah.
And I overheard them talking amongst themselves. But then I did what you did and like grouped up and had them like I guess say out loud what they thought.
Yep.
And they're good about that. Like they're not
Good.
shy anymore. Like,
Good.
They're not afraid to be wrong, but they weren't even wrong. Like they were they
Yes.
were doing good.
Yes.
Because they had just had a test that day, and I think Jordan tested them on compression. So like this is on the test.
Perfect.
So, yeah.
Oh, good. I'm glad
Yeah,
you had
great
such a
time.
good experience there. Okay. Well, finished with a bang, right? That's the
Yeah.
last field day? Okay. Very good. Hi, Roger.
How are you doing?
I'm doing well. You?
Just fine.
You're welcome to sit right in the front row. I think she's going to be soft-spoken and she has an Italian accent. So,
I just met her.
okay. So it's up to you. Right here? Okay.
Close enough.
I hope it works for your hearing. Okay.
We got a wind farm tour coming up in another week, maybe.
Okay.
Carl's.
Maybe Carl. Yeah. Yeah.
Well,
Okay.
that's where we're gonna start.
Okay. Sounds good. Okay, viewers, I assume you can still hear me. We're going to put a microphone on Debra and make sure that that's working for her. Already lost my magnet. Okay. I'd like to put this on you, please. It's something like this.
Okay.
So and I have a little, I don't know, this is where the mic is. Is it okay if I go right like
Yes,
this?
yes.
Try. And we might do both of these guys together.
Okay.
No, we're going to go like this.
Okay. Okay.
I
Thank you.
think that you're welcome. I think that's. Yeah, maybe that's it. Maybe that's it. If you're
Okay.
okay like that.
Perfect.
I think that looks just fine. So
Okay.
let's so the people at home can now hear you. So we're going to
Okay.
talk for just a second just to make
Okay.
sure they can hear you okay.
Okay.
Are you going to be here the rest of the month of May?
Yes, until the 30th of May.
Okay. And do you have a bunch of very specific things you're hoping to do with Susan's lab?
Yes. I'm analyzing different minerals within mineral dust samples
Okay.
from the ice cores.
Yes.
Yes.
Viewers, can you hear Debra? Oh, they can. They can hear you. So that's
Perfect.
good.
Okay.
So, are you you feel confident you have enough time to do all the things that you want to do?
I think
Okay.
I'll have, yes.
Okay.
Yes.
Good.
I hope that.
Okay. Well, we're going to get started in about 5 minutes.
Okay.
Do you need a restroom? Or are you okay?
No, I'm okay.
Good. So I will get everyone's attention at noon. I'll say a few quick things, then Susan will introduce you, and then we'll turn it over to you.
Okay, I'll wait here and then come.
I think wherever you want. Yeah, if you want to stay by Dad, that works. Okay, thanks. Okay, yeah, she's soft-spoken, but it'll work. It'll work. Thank you.
Here we go.
Still got a few. Please, we got plenty.
We just need to get you out there to start talking because once you get going, you'll be fine.
Yes.
Good, good, good.
I'll just go walk around for a minute. Oh no, you've got your
Yes.
in my life.
In perpetuity.
While I was in Norway last year, I came twice. So, I went to Milan and Venice to scientifically.
Did you like Venice?
Has anything been decided for a meal this afternoon?
Yeah, we're gonna do cornerstone, but we're gonna do small. So you don't have to.
Don't announce it.
The way Susan.
The man who left there.
They hate you there.
Their pizza is delicious.
All right.
I gotta worry about cleaning up.
Jordan's not involved because he's getting ready for his trip.
My sister lived in Rome for 3 years.
When do you
My
think
niece was born in Rome.
Tomorrow, late afternoon, I guess. We'll see how much Sam and Jack want to hang out down in Portland.
Okay, cool.
Like,
So
we'll
we'll
be
see.
originally
Okay.
and
Well, Jack's, yeah, he's going to the talk with his girlfriend tonight.
my
That's
I
right.
still
And you're
have
gonna just spend
I
tomorrow
think
hanging
tomorrow
out.
morning, I think so, yeah.
kind of cousins.
Get Sam involved a little bit. See how that,
But that's actually German.
Sam going to the hospital?
That's Kaspar. And then
I'm afraid to ask, but probably
yeah,
not.
so my grandmother was a Ceci, Evelina Ceci. But she came to the U.S. when she was 2 years old, and then she died when my father was a baby. So we didn't have that connection. But yeah, so I've done Florence and Rome and Naples, and I don't know where have I been. I don't know, like some of the touristy places. Yeah, my sister. But when my sister was living there, I went to Rome. She loved Rome, and she lived right next to the.
Well, good afternoon, everybody. Good afternoon. Thank you for coming. Such a beautiful day, and yet you're here, indoors. So thank you for being committed to this series. And as soon as we're done here, we will all go out and enjoy that beautiful weather. So this is the second to last talk in this series for this school year. There's only one more coming, and that is Friday, May 31st. So I think we're taking a few Fridays off. But May 31st, Lucinda Leonard will be here from British Columbia giving a talk, a tsunami talk, Head for the Hills, the potential for locally generated tsunami in the Salish Sea. And Walter Zaliga, department chair, invited her to come down. And so we're trying something new right now. Susan is going to introduce her guest, and Walter will be introducing his guest in 3 weeks. You got 3 weeks to figure out what you're going to say, Walter. Otherwise, we're going to hand this mic over to Susan. She'll introduce our special guest, and then away we go. And I'm thinking standing here, Susan, and something like holding it about that distance from your face. That's the mic head right there.
Okay.
Perfect. Thank you.
All right. Okay, well, it's my pleasure to introduce Debra Fiorini, who is visiting us from the University of Milan, or University of Milano de Bicocca.
Bicocca.
Yes, and so Debra is at the end of the second year of her PhD, and she'll tell you more about her academic background. during her talk. But I met Debra, so earlier in this series I gave a talk about my Fulbright in Norway last year, and as part of that the Fulbright has an inter-country lecturer program, and so I had started some collaborations with some Italian colleagues and had gone down to visit Debra's laboratory as part of that. So she's going to tell you more about their lab, but they have a laboratory that has expertise in dust, and so they've measured a lot of ice cores from around the world for dust, including some people may be familiar with the Epica ice core, which is, I would say, arguably one of the most valuable ice cores that we have, that provides that 800,000 year carbon dioxide record that many of you may have seen. And the lab that Debra came from worked on the dust from that. Yes. So anyways, Debra is here for a month. She's going to tell you about the work that she's doing, but we have overlapping interest in using some hyperspectral methods to look at dust. And so through that collaboration, we realized that we had this overlapping techniques that we're using that aren't being utilized in many other places. And so it's a real pleasure for us that Debra could come and spend the month. And so she got trained last week, and the joy of having a PhD student is it takes very little time. You train them, and she's already up and running and getting really great results. So I'll leave it to Debra to tell you more on her academic background, and thank you for joining us.
Thank you.
Mm-hmm.
Okay, hi to everyone. I am Deborah, as Susan said you. Okay, I am a PhD student. I work on the physical properties of mineral dust from ice cores. And today I'll talk you mainly about my PhD work that is focused on the high resolution, hyperspectral, microphysical and mineralogical analysis on an ice core that we drilled from the Italian Alps. Okay, let's talk for a few seconds about me. I am a physicist. I have a bachelor degree in physics. I have a master's degree in particles and applied physics. And now I'm working mainly I'm working mainly on the geological field, working on mineral dust from ice cores. So this is my working group from the Eurocold laboratory facilities. Sorry for my English. And this is my group. If you want to visit our website, you can scan this QR code. One thing that I like very much of this group is that we have very different backgrounds. I am a physicist. We also have a biologist. We have geologists and so on. So we can match together our backgrounds in order to reach our goals. Okay, now I can't move you all physically to our lab. So let's take a look to this video. I will talk on it. We are a lab that works in the field of polar sciences. So you can see our rooms. Here is our gray zone, so where we have the main part of our instruments for the analysis, mainly on ice cores, snow samples, and so on, from a point of view of the mineral dust. Our lab is also a depository of ice cores from Antarctica, the Arctic, or from the mid-latitude glaciers also. In our lab we have two cold rooms. The first is can reach around minus 30 Celsius, that is around minus 20 Fahrenheit. And the other cold room can also reach, this is Claudio, our technical manager, we can also reach minus 50 Celsius, that is, oops, sorry. Okay, that is, okay, it doesn't work. Okay, it will start again. And let's see it again. And we also have, as I was saying, another cold room that can reach minus 50 Celsius. It is around minus 60 Fahrenheit. And we also have 3 clean rooms, ISO 6, where we go to prepare our samples, because we also work on Antarctic samples. And due to this, we need to keep our samples very clean, because Antarctica, as we all know, is a very cold place, but is also a very clean place. So we have to not contaminate our samples when we manage it. Our clean rooms, as we were talking about, this is the entrance of the cold rooms, and this is the second entrance. And as I was saying, the clean rooms can reach also around minus 5 Fahrenheit as as a minimum temperature, but we can work also inside these rooms around in the environmental temperature mainly. As I was saying you before, this is Barbara, my tutor, and this is one of our clean rooms. This is me in the clean rooms. And okay, we also have many ice cores that we are working on. The one that I will talk you about has been cored from the Adamello Glacier on the Italian Alps. It is a 224 meters long ice core that can tell us many information about the climate history of the Alps in the last centuries. Okay, I will talk you much more during the slides about all of our instruments we are working on. And okay, I think that this is one of my colleagues. He is working on optical properties also of mineral dust using another system that is a continuous flow analysis system for the continuous analysis of ice cores and fern cores to characterize mineral dust entrapped inside. Okay, going on, this is our department. This is where I live mainly. And on the left side of the slide, you can see all the analyses that we do on our samples, from visual analysis, just looking at our ice cores, identifying different features, for example. Also to optical analysis, we will talk more deeper about it. Then microphysical analysis, mineralogical analysis, also moving to isotopic analysis, pollens and microfossils that in our case are mainly diatoms. For my work, I focus on the first 4 analyses, so moving from stratigraphy to optical analysis, microphysics, and mineralogy. My work, as Susan said before, mainly focus on mineral dust. But so, why it's important to study mineral dust? As you can see from this image as background, we have these very big blooms of dust that, as can be seen here, for example, from the Sahara Desert, are moved within the atmosphere all over the world. And we know all that the dust can affect the Earth system, in particular the optical properties of the atmosphere and of the high albedo surfaces. There are many sources of mineral dust. One of the main is the Saharan Desert. Dust has different chemical compositions, physical properties, and so on. Mineral dust, as we will see, through the slides is very present within the atmosphere and then is settled mainly on different sources from land, oceans, and so on. As we can see here, we all know that dust have a certain source, for example, a desert. It is emitted within the atmosphere, moved through the atmosphere, and then it is deposited on different surfaces. We have that the coarser part of the mineral dust is deposited at a short, let's say, medium-long distances from the source region, but the finer particles of the mineral dust can also reach a very long distances from the source region. And now let's talk about some references that also highlight the importance of the mineral dust studies. So on the right part of the slide here, we have this image that shows us the main sources all over the globe of mineral dust. As we can see here, we have mainly the Saharan Desert as a source, and as we will see, I find very frequently mineral dust from the Sahara Desert in my ice core that I am analyzing, and has been estimated also by Xiao et al. That the amount of mineral dust within the atmosphere every year, so the dust that is moved within the atmosphere every year is around 2,000 million tons. So it is a very great amount of dust. And once this dust is settled on high albedo surfaces, such, for example, snow surfaces or also glaciers, we have that there is a very strong decrease in the albedo of that surface. And as we can see here, has been estimated by Zhang et al. From the Tibetan plateau, that a thin layer of mineral dust can also increase of the 15% the melting rate of that surface, that ice mainly. And also we have to analyze the physical properties of those layers of dust, because not just the fact that we have dust tells us that we have an increase of the melting rate, but also the fact that dust can be more concentrated or less concentrated, but it also can have different dimensions if we study it at a micrometric scale, for example. And as we can see here from this graph, we have that considering different concentrations of mineral dust, fine Saharan dust particles, we have that when concentration increases, the albedo strongly decreases. So we have to know it, we have to study it in our ice core also. Okay, so let's sum up all of this, okay. We will focus mainly on the optical analysis, that is the main goal of my PhD, because we have seen that mineral dust decreases the albedo of high albedo surfaces. We will mainly also focus on microphysical analysis in order to study the granulometry and the concentrations of mineral dust in layers inside the ice core, because we have seen that also these parameters can affect the optical properties. And then we will analyze the mineralogy of each layer in order to identify minerals, trying to characterize their optical properties and to track back the source of that dust. Okay, now let's take together a long trip from Seattle to the coring site. It's like a back home for me, because we start from Seattle, Greenland, Iceland, okay? We arrive in Europe, and we reach the Frankfurt airport, for example, and okay, in Germany. Okay, it's here. Then here we can take a train or another plane to Milan, home for me. Okay, now we slowly arrive in Milan. Okay, we are in Milan together. Okay, and now we can take a bus or a car to the Adamello Glacier that is up here in the Alps. Okay, we are here. Let's talk a little bit more about the Adamello Glacier. Adamello Glacier is the biggest glacier of the Italian Alps. It is around 16.3 kilometers square. And the coring site was precisely on what we call Pian di Neve. It is around 11,000 feet of altitude. And the ice core, as I mentioned before, is 224 meters long, around 735 feet. And the diameter of the core is around 8 centimeters. The core was cored during a project that we called Climada. This project has the aim to reconstruct effectively the past Alps climate in order to make some considerations about how at a local scale it has changed during time. As you can see here, this is a very beautiful view from the refuge under the glacier, and the arrow points where we where we extracted the core. Okay, now let's start to take a look to the instruments I'm working on. This is high-res because it's much more easy to say. And this instrument is mainly, let's say, a very big scanner. This scanner can produce a very high spatial and spectral images of our fern, snow samples or ice core samples. One of the important things of this instrument is that this instrument is a non-destructive optical technique. So we can do our analysis on ice core sections, and as you can see here, our sections of the entire ice core are always around 70 centimeters long. And we can do our analysis without destructing our sample. And this instrument works at around -20 Fahrenheit, and it's very cold to work with this instrument. And okay, he has mainly two components that are an hyperspectral camera that acquires images in the visible near infrared, so around from 380 nanometers to around 1,000 nanometers. And our light source is a halogen lamp. These images that are, we will see them later, have that every pixel is characterized by a reflectance curve. So when we go to extract the data from this instrument, we mainly average on bands of pixels, extracting optical descriptors from each band of our ice core. And our band our stripe where we extract these spectra is around 2 centimeters wide in the center part of the entire ice core. Okay, this is the instrument for microphysical analysis. This is a Beckman Coulter counter multisizer for E. This instrument is special because he has mainly 3 components that are an aperture tube, 2 electrodes, and an electrolyte solution. The aperture tube is the one that you can see here in the left part of the slide, is this glass tube that has a hole on the bottom part. The diameter of the hole can be chosen due to the analysis that has to be done. In our case, it is 50 microns. This hole is in the center part of a region where we have an electric field that is generated by the 2 electrodes that you can see here are these silver parts here and here. And the electrolyte solution can help us to make our sample able to generate a signal when a single particle traverses the hole in the bottom part of the tube. Mainly the physical process works when a single particle from our melted sample that we have here traverses through the aperture and generates a signal that is proportional as an impedance, that is proportional to his diameter. A particular thing about this instrument is that he works considering that every particle has a shape that is a sphere equivalent volume. And as you can see, it is an example like this cow. If we could throw the cow inside our tube, also if she has all the shapes, different surfaces, the Coulter counter could see this, a spheric cow, let's say. Okay, this is another instrument, the first that I will talk you about for mineralogical analysis. This is an X-ray diffractometer, XRD. It's more easier for us. And okay, as you all know, this instrument has an X-ray source that is an X-ray tube, and when we do our analysis, we have to place our dust on supports that must not affect our data. So in our case, we consider silicon discs. These discs, when are exposed to X-rays, are background free. So we can see our dust, we can do analysis in a qualitative way in order to identify the main mineral groups that are inside our samples. And the physical process that this instrument considers is a coherent elastic scattering due to the internal lattice of our minerals. Now let's talk also about this instrument. It is a Raman spectrometer. If you want, there is here the QR code of the website about the group in our university that is working on provenance studies mainly. And okay, the instrument is that you can see here, and it has a microscope, this, and a laser source. The laser source can have different wavelengths. In our case, it is 532 nanometers of wavelength. And this instrument can tell us a single grain of mineral dust which mineral is. So we can point our laser to a single grain of mineral dust, and we can say, okay, this is quartz, for example, and this is very important for us. And this instrument works mainly considering intra and intermolecular vibrational modes. As you can see here in the bottom part, I don't know if it will work again. Okay, we have the molecule that forms the material that we are analyzing. This is our laser, and the molecule starts to vibrate and then to excite, emitting Raman scattering. And so we are analyzing these photons to characterize the material that we have inside our samples. Okay, this is the instrument I'm working on here at your university. This is a very special instrument for me because, as we said before, my optical result from the hyperspectral system is produced by a very large amount of dust particles, but here I can analyze a single particle of dust, and this is very important. So this system can tell us the reflectance curve of a single grain of inside an ocean of grains. The analysis is made considering some resin packs, standards resin packs with minerals that we know perfectly which minerals they are, and also on real samples from the ice core. And so we can put these resin packs under the microscope, and we can not only extract a single grain. Okay, now let's see some data. Okay, now we start from the hyperspectral system data that I'm working on in Milan. And on the upper part of the slide, you can see a composition of images from the hyperspectral system. This is the result from the images, highly resolved images. And on the left side here, you can see the reflectance spectra of different regions of this portion of our ice core. And as you can see, different features inside an ice core can vary very strongly the reflectance signal, because as we can see here, inside the red rectangle, we have a very dark layer of dust, and this is the curve that he produces from an optical point of view. And we have also, for example, bubbled layers and ice lenses. So we see that not only mineral dust can vary the optical properties of an ice core, but also the internal ice features can vary it. Okay, these curves are used through some softwares to extract optical descriptors. These are our optical parameters that we extract, and the upper one is the albedo that we all know about, and the second is very hard to say for me. It's snow darkening index, I'll say SDI, and the third one is the impurity index. Okay, so the SDI is very sensible to also very small variation in the darkening of ice. So this parameter can tell us, for example, through this peak that is in the region at the depth inside the ice core where we have this dark dust layer, can tell us where we have those dust layers. And the third not only can tell us how much dark is that portion of the ice core, but it is also sensible to the internal features of the ice. So let's say, for example, it is sensible to ice grains mainly. So we are still trying to work on it, but this is also a very important parameter to be extracted. Okay, so we have seen here that we have this very dark dust layer, and thanks to the SDI parameter, we know that we have it, and we know, or mainly we can analyze how it is concentrated and how it is darker through the mineralogical analysis. And so we can select small samples from the ice core, we can melt them, and then do microphysical analysis at first. Microphysical analysis from the Coulter counter can produce these distributions. We have, as an example, on the upper part, a number size and the volume size distribution for a very low concentrated sample. As you can see here, we have a very small amount of particles per milliliters. And in the bottom part, we have the same thing, but for a very high concentrated sample. As you can see, just by eye, the difference is very, very clear. But we use, in particular, volume size distributions to obtain information about the diameters of particles in our samples and their concentration. And as we can see here, this is a very concentrated sample, as the previous one at the bottom of the slide. And our analysis starts here mainly to consider how many particles per milliliter we have inside our samples. And then we can estimate the concentration in ppm or ppb to see how a different concentration can impact on the SDI that we have seen before. We can also consider, for example, a granulometry also in a different range of our particles, as you can see here from the pie chart. For example, we can observe that we have finer particles that can be considered from 1 to around 5 microns. These particles are in the middle region, so I can say not finer but not coarser particles, and they are here around 5 to 10 microns. And then the coarser portion of the particles here from 10 to 30 microns. And just from this we can infer about, for example, a local transport due to a very great amount of coarser particles that we have inside these dust layers, but also a finer portion that has to be considered. We can consider that the finer part of our dust layers mainly can arrive from the Sahara Desert. We will see better than this. Okay, this is quite difficult to explain, but I can try. This is a simulated curve that we can extract using a regression model overlapping the optical signal from the SDI and the concentration data from the Coulter counter. Okay, what you are seeing here is an extracted concentration from the model that can tell us, teaching to the model the optical signal that he can see when we have dust inside of our ice cores. He can say mainly where we could have other dust layers without melting other ice. For example, we have seen before the SDI signal. Okay, it is an optical signal that can be used to simulate, thanks to the red crosses that are our data from the Coulter counter, so are the real concentrations of these dust layers that we have seen before from the Coulter counter. And we use this optical signal to teach mainly to the system how to simulate other dust layers inside our ice core. So the yellow peaks are the peaks that has been used through their optical signal to teach to the model which is the optical signal when we have dust inside our ice cores. And the purple peaks are those that has been simulated by the system, because he says, okay, due to this, we know that here we could have other dust layers, and they are real. They are there. And there is a very particular thing about this graph, because if you can see here, the red crosses here are quite in accordance with the optical signal, but here it's another history. It's another story, because here we have a very dark signal from the optical analysis, because these peaks are higher when we have a darkening inside our ice core, but the concentration is very low. So what can we say about it? Our considerations are not passing through the concentration, but the mineralogical composition of that dust layer. So that's why also it's important to extract these data from the XRD. This is the raw data that we can observe from an analysis from the XRD. What you are watching at here is an overlap of 3 different samples, 1, 2, 3, sorry, here is in Italian, but okay. And okay, then with a search and match procedure, we can identify the main mineral group inside our samples. For example, we have here muscovite, biotite, quartz, and so on. We use XRD mainly to identify a possibility to local rock-forming minerals, let's say, presence, for example, and also a finer part of our dust, dust sample that can be tracked back to the Saharan desert. And let's say for us, one of the markers from the Saharan desert is a secondary mineral, a secondary formation mineral, that is the kaulenite. So here we can say at a first consideration, we can see a local transport, but also a long distance transport. But another important thing about these results is that the shape of our peaks can also give us further information about our sample, because we have that the width of the peak can tell us information, but also his position, that is the parameter that we use to identify minerals mainly, and their intensity. So let's say the width of each peak can tell us information about the presence of defects inside the lattice of our minerals. The intensity can tell us the concentration of that mineral, and also, for example, the presence of impurities inside the lattice, and so on. Okay, in the previous slide, these three spectra were overlapped. Here we can look at them separately. And as you can see, the first two samples are very similar, and both of them have a quite amount of kaolinite, but the third sample is very special for me because it has, a small amount of local transport, for example, from muscovite, biotite, and so on. But also, as you can see from the left part of the slide, from the pie chart, here we have the relative abundance of each mineral group that we can observe here. And there is a small amount also of calcite, but a very great amount of halite. So this is very special, and we are analyzing it yet. Okay, now moving, we can move to a much smaller scale. These are the data from the Raman spectrometer. And here, for example, you can see one of the resin packs that we created with the dust inside. In the upper part here, you can see a single grain from one of the resin packs that we used for standard minerals. In this case, we have rutile, for example. The result from Raman is mainly this. We have Raman shift, and we have intensity of each peak. And using a reference, a standard source that we call roof, we can say, okay, we have these peaks, and they seem to be I don't remember the word, but okay. We have these peaks, and we can say, okay, we have inside these packs effectively this mineral. But we can do this work also on real samples. You can see on the upper part here a grain of quartz from the ice core that I'm working on, and this is the spectrum that we can observe from this grain. And in the bottom part here is a single grain of one of our standards, and you can see here that the spectrum is mainly the same. So this is a very great instrument to identify different minerals. But it's very special also for me, because what you are looking at here is a very strange thing to analyze, because as we have seen here, our spectra of different minerals mainly is in the left part of the x-axis, but what we have observed here is this spectrum. So here we haven't mainly anything. We have here these two small mountains, and after a baseline we can see this. Okay, so after the usage of a smooth function and a fit, we can obtain these data. So we have effectively these two peaks, but I'm working on minerals. So what is this? And looking at here, we have the two centers of the two peaks, and from the reference here, we can observe organic material. So from the ice cores, we not only are looking at minerals and so on, but also to organic material. The very important thing is that when we analyze minerals, we can use our laser also at 50%, for example, of its power. But when we work on organic material or on, for example, also some materials that we don't know what they are, we have to, as you can see from here, we have to reduce the laser power to around 1, maximum 5%, in order to not destruct the sample. With the Raman, we can also make maps of our samples. I haven't reported it here, but this is a surface of our sample. This is around 1,000 microns. This is a surface, and from here we can extract this small image, and we can create a grid with all of these small squares that are the small regions where we did the map, mainly. So we can, let's say, extract like a thermal map of our minerals inside regions of our sample. Okay, now we are finally to the HIMS results from the instrument that I'm using here. This instrument is very important for me because from the Raman I know each grain which mineral is, but I can't know which is his optical signal. This instrument can tell me this. So here you can see an optical image of a grain of from one of my standards, that is the hornblende. Here you can see the hyperspectral image of this grain. Here you can see how I select the region of interest inside the grain in order to obtain his reflectance spectrum. And here you can see 5 reflectance curves from 5 different grains inside this resin pack. And when we average through them, we obtain one single curve that has all the features that are important to characterize that precise mineral. So what you are seeing, what you are watching here is the reflectance signal from the hornblende of our standard. We are doing this work with 15 standards and further real samples from the I-score. Okay, now as an overview, we said that we have reflectance curves from the I-score. We have these parameters that we can extract from I-scores from their entire length. We have these peaks from the SDI parameter to select samples for the microphysical analysis that can tell us information about the concentration and the granulometry of dust inside our samples. The XRD can tell us mainly which are the main mineral group inside our samples. Now we can see this example that is for the quartz. So for each grain we can extract with the Raman our spectra to say, okay, that is quartz. And here I can, on those grains, extract also their optical signature. So thanks to this, we can say mainly that the hyperspectral system is a non-destructive system that can be used to extract the optical signature from ice cores all over the globe, from Arctic, Antarctica, and so on. In our case, from a mid-latitude glacier. And okay, microphysical analysis can tell us the concentration of each sample of dust and their granulometry that, as we have seen, impact very strongly on the optical signal. And the XRD, Raman, and HIMS can give a complete characterization of our samples from a mineralogical point of view. So, if we consider the first two, the hyperspectral and the microphysical, we can say that the matching of these two instruments can also help us to signal from portions of ice cores and snow samples, for example, without melting them. So it's very important for archives. And we can identify mineral dust layers and analyze them through the Coulter counter. And these mineralogical instruments can give us many information about qualitative and quantitative mineralogical information, and also can help us not only to analyze their optical impact on albedo, but also to track back their source, the Sahara Desert, for example. And this is very important for me because my PhD mainly focus on an interdisciplinary approach to analyze mineral dust and snow samples, fern samples, and ice cores. So for me, the usage of many instruments can allow to see all of these to a very complete point of view. So I want to thank for all the persons that are helping me during my PhD. This is the big boss of our university. This is my tutor, and so through them. Okay, this is all, and I thank you for your kind attention.
Thank you. A few questions for Debra, and I think Susan's going to repeat your question for the home audience as well as just give Debra a second chance to hear the question.
Go ahead, Chris.
Debra, I really love how you're integrating so many different techniques.
Thank you.
I was really impressed by your halite sample, and I was wondering if you could just talk a little bit more about how you prepared the sample in order to not destroy the halite.
And
Okay.
I'll just repeat for the home audience. So the main question Chris was asking is how you prepare the halite so that you don't destroy it.
The samples that I use for each of them, or for optical analysis in a precise.
The XRD specifically.
Okay. So I select through the SDI signal that volume of ice. I have to melt it, and then I use. Can I turn back? Thank you. I will show you. Okay, it's far away, but I will reach it. Okay. Okay. Here. Okay. So when the sample is melted, I use a small filter to concentrate the dust on this filter, and then I put it inside a I don't know how it is called, but a vibrational,
Like a sonicator?
Okay, exactly, a sonicator, and each grain is then free inside a very small amount of water. In our case, is hyper pure water in order to not contaminate our samples. We do the entire ITER. I don't know if it is called so, but we do all inside our clean rooms. So in a very clean place, and then I haven't a photograph of it, but we then use an Eppendorf, okay, a pipette, okay, a pipette put these mineral dust on background-free silicon disks. And so this is the main procedure that we use. We can talk about it also later, if you want.
More questions? Well, I'll tell you what, why don't you come on up afterwards and visit with Debra if you've got some more questions, but let's give her another round of applause for her.
Thank you.
Take some Vinmans on the way out. We'll see you in a few weeks. Thank you. That was an excellent talk.
Thank you.
Thank you.
Thank you.
Anna Shamlou and Susan Kaspari chatting with our guest speaker, Debra Fiorini. What's happening? Why can't I turn this camera on here? Okay. Well, thank you for joining us live for this lecture. This series continues. Special thank you to those of you who supported this series specifically. We will continue next year, Hannah Shamlou and I, putting this schedule together. But for now, we have one more talk. So we have the last talk of the whole series for the school year is Friday, May 31st. Lucinda Leonard, Head for the Hills, the potential for locally generated tsunami in the Salish Sea. So mark your calendars for that. Otherwise, we're taking a couple of Fridays off. We have a Geological Society of America conference, Rocky Mountain / Cordilleran section meeting in Spokane most of next week, so most of the department will be in Spokane for a series of talks and other things. And then there's Memorial Day weekend in there, and there's something else I can't remember. But we've got plenty going on here. I'm sure you do too. And a few of you I will see this evening in downtown Portland. So I need to run right now. And please, tell all your friends to stay off of the freeway in about 3 hours in downtown Portland so I can get to this talk on time. Okay? Great. Otherwise, thank you. I love you, and we'll see you 3 weeks from now. I think that's what that is. 3 weeks from now. Thank you. Have a good day. Goodbye. I'm not going to say I love you because there's still people. I love you.